So this morning, I'll be talking about the importance of R&D, particularly relative to NDE, how that applies in an industrial environment, and some of my personal reflections on it. These are my personal reflections, not the views of Pratt & Whitney or anything like that. So that's my disclaimer. So if anybody wants to say I violated my non-disclosure, that's not true. So Tom, calm down. So moving on. And as Gavin mentioned, I've worked on a lot of projects going from the R&D phase through full implementation, and some worked out, some didn't, some stopped early. That's all part of the game, and we'll talk about that here. I'm obviously not going to have specific examples, but at any rate, that's what I'll be discussing today. So we all know that technology continues to advance in general, but in NDE in particular, it's certainly changed a lot over the unfortunate decades of my career. And in terms of what we can actually do today, the tools we have to use are better. I mean, the physics are the physics, but the tools we have to use to be able to implement solutions are a lot different than they were back when I started my career. And I'll avoid the temptation of talking about what the instrumentation I first worked with was like, but you didn't actually have to hand crank it, but it was close. So the point of all of that is that continuing to invest in R&D is a really important thing to be able to maintain the technical health, whether you're in a research organization, an organization that uses NDE that's critical to their function of their product, or an equipment supplier. So, and failure to invest actually really results in going backward. If you stand in one place, everybody else moves ahead of you, so you're really going backwards if you're standing still. So that's been my viewpoint for a long time, and I haven't changed. So in terms of approach, there's several key elements that I've found to be very important over the course of time. One of them is first to have a plan, and I'll be talking about a technology plan, or at least my view of a technology plan next. I think that's an important thing if you're going to have a going forward approach that's going to have some continuity to it. Having a plan is an important thing. The R&D directions need to be tied to something that's relevant to the customer. That's pretty obvious. I've seen situations where that wasn't always true, though. Take rational risks. Moonshots are pretty seductive and really sexy, but they're going to fail more often than they succeed. So that's something to be careful about in terms of how that's all being approached. And then there's, of course, the valley of death, where you can go from having something that shows good feasibility in the lab, and then there's a lot of money that's got to get spent to get it into implementation. And bridging that valley of death is important. I'll talk some about that. Anybody that's ever worked with me knows that I'm a demon about technical rigor and the importance of being technically rigorous in the development, the documentation, and so that we understand what we're doing, and we don't end up in situations like reminiscent of the old Stevie Wonder song, you believe in things you don't understand and you suffer. So that's something I've co-opted for a while. So, and then of course validating and quantifying the inspection is an important thing as well. And I come from the aerospace engine industry, so it's particularly important there. But it's obviously, anytime we're doing NDT, there's a safety implication, so it's important everywhere. I can't speak as rigorously to other industries, but it's very important there. One thing that is always discussed is the technology readiness level progression, and it's a useful process, and it's very rigorous. There's some observations that I have about applying it properly so that it actually does what it's supposed to do, and this is kind of experience learned through significant pain, so I remember it really well. One of them is that the way TRL works is that it's a gated process. So there's work in a stage, and that results in a gate review, and then once that gate review is passed, then you go to the next stage, et cetera, until you're done. And so, which is great, but to actually apply it properly, there have to be criteria. So there are general criteria in the TRL documents, but it needs to be tailored for this specific project. And so those criteria need to be defined in a way that are particularly meaningful to the gate. And if they're softball type criteria that are just easy to pass to get through the gate, what that does is it snowplows all the risk to the end of the project, and that can result in catastrophic failures of the technology and a lot of embarrassment and frustration. So don't want to do that. That undermines the whole process, and there's not much point in doing it if it isn't carefully if it isn't structured in a way that's to mitigate risk. There's also review teams at these gate reviews, and that's always, in my experience, a difficult thing in NDE because there's not very many NDE people around that understand a particular technology, particularly at the R&D level. So, like in a company, everybody that can contribute is working on it normally. So then when you go to do a gate review, who do you invite? Who's going to be the reviewer? It can't be the people that are working on it. It needs to be somebody else. So who's that going to be? Well, if it's people that don't really understand what the technology is or understand the criteria or what the criteria means, then bad results can happen. Can end up with situations where you get action items you can't close. So now what do? You just sit and spin. And that's not good. Or they can just get passed because people want to pass it and they don't know any better. It's not that they're ill-intentioned necessarily, though I have seen that happen too, but but they don't understand the criteria. They kind of get snowed by the presentation perhaps, et cetera. So that's, sorry about that. Yes, I should be advancing the slides more quickly, right, Tom? So anyway, it's not well suited for emergency projects because that structure and in the various presentations just have to get created and presented and meetings organized and all of that take time. And so if you're trying to go really fast, it's not a great process for that. It definitely slows things down a lot, which in most cases is okay. Emergencies, it's got to be careful. So anyway, back to technology plan. The technology plan is, in my opinion, a communication tool. It needs to be something that you can talk internally to, or talk to the customers of this technology. People are going to be putting up the money, and also to help organize what projects are most important, how long they're going to take, where does the money need to come, and all that type of stuff, and what the benefits are. So it's one thing you'll hear me come back to a number of times is that it's really important to tie the customers into what you're doing and keep them updated so that you avoid surprising them. Customers are a lot like the stock market. They can take bad news, but they don't like to be surprised by it. And surprised bad news is really, really bad. So it can result in a big thing, and it undermines credibility too. So it's a communication tool. Keeping it updated annually, it's not. I view it as a tool, not as a museum piece. So keeping it updated and use it. So then of course in that technology plan there's going to be a risk in all these projects. So I recommend there's a spectrum of risks that are represented in it. Some of them are very high risk, high return, the moonshot type of projects. My opinion is that ought to be out on the tail of the distribution, and things that are like real close to implementation. There's going to be some of those because projects will be maturing and ready to go into implementation, so that's fine too. But the majority of the stuff needs to be in I'll say the intermediate term, where it's where people can see a light at the end of the tunnel that hopefully isn't an oncoming freight train. So critical to identify the key technical risks early on. This is, obviously fairly obvious, is that if you got risks, you want to start working on them right away because they can hang you up and be real big problems. And then also critically review which projects you have on your technology plan annually. There may be things that the need has dissipated. You don't want to go off and leave the water running on something that's no longer needed, obviously. And also some R&D is a learning process. So there may be something you learn that says, okay, well, we thought this was a great idea. We did X, Y, Z, and we found out about this other thing that really makes it not appropriate for what we're trying to accomplish. And so being upfront and discontinuing ideas that are not working or no longer relevant is important. That helps, one, it gets the resources applied where they're most useful, but then also, and that's people as well as money, but then also the other part of it is that it's good for credibility if you're the one that's saying something isn't going to work as opposed to having your customer prove it to you. So that's my view on it. So relative to technical rigor, identifying the unknowns that are going to pose a risk needs to be worked on. And as you do the work, and we all know this, you do the work, there's going to be stuff that comes up. It's like, oh, gee, I didn't know it was going to do that. Now, why? What do we do about it? Is this a real problem, or is it just a minor inconvenience? And being clear on that, and then keeping that information documented and well organized, so that if the technology goes all the way through to the end and you implement it, you have the basis of your understanding is there, and you can answer questions readily as opposed to repeating experiments, which is not any fun. But then also, if the technology ends up not getting stopped along the way, later on, if it's important to revisit it, or somebody just is unaware of it and says, well, what about this? Well, we did this, X, Y, Z, and here's the results of how we got to where we got and the conclusions we drew. It saves a lot of time and money in that process, and it creates some sort of a record and a legacy, so it keeps people doing new things instead of repeating the same thing again and again. So now validation is a big thing relative to safety critical aspects, and I've got quite a few slides on this, so if you start going to sleep, I'll advance the slides more quickly, so that'll be my cue. So at least in the work that I've done with my organization, there's always deterministic studies, and what I mean by that is, lab scale samples, something you can hold in your hand more or less, that helps you understand what the basic concepts are, or basically how the technology is performing. Works, on the basic stuff like sensor selection and I'll say the very basic aspects of feasibility, and to work through those things. And so these things can address issues that you may be particularly concerned about. In my world, things were things like coverage, edge effects, signal-to-noise ratio, either from surface finish or material characteristics like grain size and precipitates and all that kind of stuff. Those may be the primary things, but it could be other things that need to be looked at that are going to ultimately be able to affect the real approach, the viability of the solution. And there may be that there's different sensitivities in different zones of the part, and that's an important thing to know. More to come on that. So one of the things, at least in the world I lived in, and it may not be true for everybody, is that there's frequently there's no naturally occurring defects that are still intact to work from, like in an emergency project. So that leads down the path of artificial defects. So now what? Well, there's you have to find one that's appropriate, and having it appropriate for the NDE physics is critical. Obviously, if it doesn't represent the physics of the inspection in terms of how the ultrasound, for example, is interacting with the crack, then it's not an appropriate artificial defect, and you got to think harder about it. But then there's other factors that like residual stress and crack closure effects that can affect response as well. Artificial defect may not have any, maybe like an EDM notch that's wide open versus a crack that may be held closely together by shot peening or operationally induced residual stress or whatever that can affect responses as well. So it's kind of a complicated thing to get right. And of course, when we start talking about quantifying these things in a probability detection study, we ultimately want, what everybody wants to know is, for the actual defect, what is the probability of detection versus the actual crack size. That's the important thing. They don't care about what is the probability of detection of finding a flat bottom hole or an EDM notch. It's kind of irrelevant because we don't have those. So I won't go into any detail here, and I'm sure I'm hearing the sigh of relief any moment of creating the transfer function between the artificial defect sized response versus an actual crack. And there's methodology that's been out there in the public domain for probably 30 years now. So it's not something you can't figure out, or read about. But anyway, that's a way of going about it. There are also model-assisted approaches and other things I won't talk about. So then the question I got asked a lot in my career was, well, why do POD? We don't need to do that. This just takes time, it takes money. Why do we have to do it? Well, it's very rigorous, and one of the there's two really important things about all of this is that the POD curves, if there's a safety risk analysis being performed, that's an input that people really need to have. So as opposed to a guess, it's a quantified value, and it also I found it very helpful in addressing weaknesses in the inspection that certainly I didn't know about until we did the POD study, and it's like, oh well, that didn't turn out as well as we thought. Well, why is that? And dig at it some and make some improvements, and then redo a blind test to see if it really did improve the situation or not. So it's a valuable tool. I've always found it to be very useful in terms of producing a good product that we understand at the end. Reference Stevie Wonder quote. So relative to POD, like I said, one of the big issues is how long it takes to do, and starting from the design of the POD to actually doing it is always an issue. So start early, and then where that typically is going to have to start with is definition of the artificial defect, which I talked about some already. I've seen situations where the ideal artificial defect is something that's a development project in and of itself. Like, how do you make an embedded crack in a full geometry? That's a really, really difficult thing to do. So is there an alternative? And all of these things come with trades. Like trying to do something, simulate an internal defect, maybe you introduce artifacts that create big problems. Maybe they don't, but that's all part of the trades and the engineering aspect of doing this type of a thing. Then that leads to a POD design, and I recommend Mill Handbook 1823 is very good guidance for that. I wouldn't recommend, if you don't understand this, just going off and doing it on your own. I'd recommend seeking professional assistance so you don't get wrapped around the axle on it, which is a pretty easy thing to do because there's a lot of statistics in the whole issue that have to be carefully addressed so you don't violate the fundamental assumptions of the analysis. One of the very important decisions to make is this is going to be a hit-miss type of analysis or a hat versus A analysis. A hat versus A hat means defect response, A means defect size. So it's not as mysterious as it sounds right off the bat. But like, for example, FPI is an example where a hit-miss approach is appropriate and an A-hat versus A is not. So where frequently eddy current, it would be an A-hat versus A approach is appropriate, and they've all got traits associated with them. Another thing that can be an issue is that over the inspection area, there may be different sensitivities in different zones, which means you probably ought to plan on essentially 2 POD sets to address those 2 zones. Is that painful? Yes. Is it as painful as finding that out at the end after you've done all the stuff of manufacturing the POD set, doing the testing, and then find out that now we need to go back and make some more defects? That's an order of magnitude more painful, at least. So we'll move on. So manufacturing the POD set, that's a complicated, time-consuming process. There'll be probably anywhere from a minimum of 40 defects to maybe a couple hundred, depending on all these factors I talked about earlier. So finding a manufacturing source that can actually do the work and not create a bunch of noise in your system that you have to essentially rework. You don't want that. But that's not as easy as it sounds necessarily, because doing this kind of, I'll say, relatively precise work is not that easy on particularly like full-size parts. So that's something to be careful about. And then like defect placement, orientation, and size are critical. If like say for example, the defect orientation is this, but the manufacturing source ends up putting it in over like a 45 plus or minus 45 degree range, and you don't find that out soon enough, big problem. Or can they do they can do the defect you want in a small sample, but they can't do it in the full scale piece that you need. That's another problem. So well, just things to keep aware of. I mean, none of this stuff is revolutionary, but it's something to consider. And then do the runs. Start off with a relatively few number of people that do this, and there's going to be teaching people what the inspection is one thing, and they certainly need to understand the draft procedure. But then there's typically in POD sets, there's going to be some non-idealities that have to be accommodated by the inspector. Like if there has to be an access hole, they shouldn't be calling the access hole as a defect. They have to know that and know how to document things so that the data can be reduced readily. Also, the ergonomics are important, particularly, well, certainly in situations where the ergonomics are key. Like, for example, in the engine world, we send people up the tailpipe, down the inlet, through borescope ports or whatever in awkward positions. And if that isn't captured in the POD, then it's can result in a anti-conservative result. And so a good mock-up that represents the ergonomics is something well worth considering. So then you get the data, maybe you make some improvements, as I discussed earlier, and then finalize the inspection and start doing your final POD testing. But you'll also want to do some field trials. So I'm used to dealing with fully assembled engines mounted on aircraft. So this is kind of from that perspective. I realize that isn't everybody's world, but there's probably analogs to that in things that most people do in this industry that deal with the field anyway. So there could be situations where the people that are supposedly the experts on the fully assembled thing don't appreciate that there may be variations that are not full model number changes, but creating situations where there's interfering hardware, which can be a big problem. There also may be things that cause false positives, like some contaminant that you haven't seen in the studies up until that point. So those have to be addressed because they can affect where you put the the threshold. So in an ideal world, you could have a really great POD, but you can't really put the threshold that low, or you end up with an unacceptable false positive rate. And what's acceptable for false positives, that's really case by case and industry by industry as to what the tolerance is, where the gag threshold is going to be for false positives. So one thing about doing field trials that's always entertaining is that the customers are extremely interested in what's going on, because there's new equipment, new faces, what's going on, why are they doing this, and so having a communication plan worked out, and who's going to answer the questions, how are they going to get answered, and all of that, so that everybody's on the same page before the team goes out to actually conduct field trials. Like always one of the questions is, well, what are you going to do if you find a crack? Because you haven't released an inspection yet, this is a trial. And so that can have a variety of answers. But I can say that on more than one occasion, I've seen situations where the actual thing we were looking for was found during the field trial. So it's not just a hypothetical thing. It happens more often than I would have guessed going into all of this stuff. So in conclusion, R&D is a long journey, and it requires a lot of persistence, adaptability, and patience to get through it, because there's going to be frustrations. It's a learning process, so you don't know what you're going to find out. You know you're going to find something out, and you have to work through it. And if you're not prepared for that, it'll be a big surprise. Keeping the customer involved, having frank communications with them, so that you have credibility, and that can help you get through the valley of death between feasibility and being able to implement something. Technical rigor is really important. I talked about that quite a bit, and I talked more about validation than probably any of you wanted to hear, but that's critical to successful implementation. So the bottom line is that I'm a strong advocate for doing R&D and NDE, because if you stand still, you're in effect going backwards. So that concludes my presentation. Thank you.